Hi, I'm Miguel Ángel Rodríguez, and I'm going to show you how to use URDF files in ROS. So you're going to learn basically how to use them, why do you need them, and what can you do with them. So we're going to use Robotics Academy platform to access that platform. You just have to go to theconstructsim.com and click on Robotics Academy, and here you just have to sign up for free if you don't have already an account, and if you do, just log in, like in my case. So sign in and you're inside. So here you can do many courses. So in this case we are going to do the robot creation with URDF ROS. So just click start course. Once you have all the simulation loaded, you should have something similar to this. So let's do it a bit bigger. So you'll have a tiny 2 walls and some columns, and then you have 3 very distinct different robots that we are going to work with in this course. So we are going to work with Gazebo, which is a model created by Cynthia Britziel and its team, and basically it's a 3 degrees of freedom robot. That it's a social robot, and we are going to build it from scratch. Then we are also going to build this tripod robot, and we are going also to work on this very cute egg-shaped robot. These 2 robots are inspired on 2 robots created by Alonso Martinez. It's a worker in Pixar, and if you haven't seen its robot, I highly recommend you that you have a look in YouTube. There's a link down below. So that's it. You're going to learn how to build these 3 robots. So let's have a bit of fun, shall we? So the first thing we are going to do is launch the robot party. So these 3 robots are very, very different in movements and in its morphology, but actually you learn most of the knowledge to create all of these with Mira, this very basic robot, but all the knowledge can be applied in the same way to this 3-legged robot or to Gazebo, exactly the same. So you're going to learn how to build them and make them move, also to define the physical constraints like friction and so on. As you can see, for example, you can also access some sensors. For example, if you execute RQT image, we are able to see the cameras inside the robots. So in this case, Mira, the egg-shaped robot, and Gazebo have their own cameras. So we're going to have a look at the images in Mira. So you have to be a bit patient because the connection will be a bit slow until it's established. Once it's established, you'll have a stream of video, more or less constant. There we go. So it's around 15 seconds or so, depending on your web connection. So we are seeing exactly what Mira is seeing. Yep, there we go. Very good. So let's have a look. Let's stop the party. So why do you want URDFs? Well, there are two main applications for URDF. One is what you're seeing now, so create your own models of robots and then simulate them in Gazebo. It's one of the main attractions of this. But the other one is you have a physical robot, but you need to use some ROS packages like TF and so on, and Robot State Publisher, that need a URDF definition. They need a definition of how the robot is linked. How many links, how are the joints, what morphology are the joints, prismatic, rotational, they are fixed, and so on. And you need to define the model. You are using the real robot, but you need to define it for some calculations and some programs that ROS uses. Very basic ones, actually. So, ready? So let's dive in. So while we wait for the simulation to load, we are going to talk about what are we going to do in this unit. So what we are going to do in this unit, first one, is create this egg-shaped robot called Mira. Only the outside, let's say. We're not going to simulate it for the moment. In next unit, we are going to make the modifications to this URDF file in order to get this robot in the physical world, in the simulation. Yeah, so let's have a look. So the first thing we're going to do is create the package. In this case, I've already have it created. So you'll have to create, let's have a look. Here. So here we are going to create the package. So you'll have to create a package like catkin create package, the name, my Mira description, and so on, and the dependencies. Bear in mind that if you don't know what I'm doing, you should do first ROS Basics course. Okay. So once the package is created, we have to do some minor things. The first thing you'll have to do is create your directory called URDF, and inside it create a file called Mira URDF. Yeah. So here you have the most simplest URDF that you can create. It's made of, you have this definition of the XML version, that's just for syntax. Then you have this tag, which is robot, the name, and the name of the robot, in this case, Mira. Yeah. When you spawn the robot, you'll use this name, so you'll have to know which name you have written here. Then here you have one link, two links, and a joint. This is the most basic structure that you could find in a URDF, that it's not just a block. So this is the simplest movable robot that you can create. So you have a basic, always you'll have a base link, the one that you start. Here you have the definition of the visual. So you have what's the shape of this link. In this case, you have a cylinder of radius and length. So you can use in geometries, you can use cylinders, spheres, and box. Yeah. Here you have a second one, which is the roll M1 link. That it's also a cylinder of these dimensions and so on. It's exactly the same, as you can see. And then you have the joint. The joints connect different links. In URDFs, there's a basic limitation that you can't do links that are parallel. So they start in the same point and then end in the same point. You can't do that. In SDFs, you can do it, but in this case, in URDF, you can't. So you have to bear that in mind when you design robots or when you are going to use URDFs. But in most cases, it's strange that you need that, and you can change a little bit the simulation so that you don't need the structures most of the cases. So as you can see here, these are the three options that you have for basic geometric shapes. Yeah. So let's do it. Let's have a look. So one of the things that you need is some way of visualizing the model that you're creating. Otherwise, it's very difficult to create it, because as you can see, you have a link, and then you have a joint, which in this case is a revolute, so it's one that turns, and it's connecting the base link with the roll link. And then you have these numbers, which is where you position this joint, let's say this, and then you have some limits and so on. But this origin is really important because it defines where you're putting the joint, and therefore the geometry and how the shape and the robot will look. And these dimensions are really difficult to get if you don't have any tools to see what you're doing and to validate if they are correct or not. So for that, we're going to do a simple launch that basically what it does is spawn this URDF using RVIZ, and you can visualize the model of the robot. And not only that, but you can move the joints. The same thing, if you if you don't understand this code, you should do our course in TFs, because we go more in depth on what we're doing exactly here. Just bear in mind that we are publishing fake joints values so that you can move it with a slider. So let's have a look. So let's execute this command, because I've already created this launch in my case. So if you go to meta description, I've created here, I have loads of them, but one is this URDF visualise. Yep. Which basically is getting the model, publishing some joint states, and then executing the robot state publisher and running RVIZ. Okay? So let's have a look. Let me do it like this. So we go in here, we do our source just in case, and then let's do something like that, and I'm going to select my URDF. In my case, I've used another name just to be more explicit, and I have this simple meta, which is the one that I showed you before, this URDF file. Yep, understood? So I'm going to get this simple meta, and that's it. So now I've executed RVIZ, so I'm going to the open graphical interface, and here you have two windows. One is the RVIZ and the other one is joint publisher. So we'll put this always on top so that we don't lose it. And then we have this simple RVIZ. So what I'm going to do is add firstly a model, very important, robot model, which it was loaded in the param server. That's why we have it. And then I'm going to load also TFs, which are published by the robot state publisher. As you can see, there's nothing, there's a white thing, so cylinder, we should see a cylinder, but I'm not seeing it correctly, and the TFs are giving errors. That's because I have to select the base link. In my case, and in your case, we only have two. So we select one, hit enter, and we have it. So by default, the geometric shapes are in red color, but you can change it, and you're going to learn how to do it in no time. So with this, you are publishing the joint states, and this is very useful to see if you define correctly the joints. Why? Let's have a look. Let's validate. There we go. So here, let's have a look at axis. Here, I'm defining which axis I'm rotating. In this case, is the X. Let's have a look. If I change the value, it's rotating around the X-axis. X is the red. It's using the RGB order, so red is X, green is Y, and blue is Z. Yep. So I'm seeing that it's moving correctly. Not only this, but you see that I can't move more than that, than minus and plus 0.2. That's because I've defined a lower and an upper limit. This is more related to physics and movement, related in simulation, so don't worry about this for the moment. But here is what's the limits in the joints, because in a real robot you can't turn normally 360 degrees. Normally there are some things and some motors that you can, but in that case you'll put not revolute but continuous. Yeah. Okay. So that's quite it. Another tool that it's really important and very useful is this one. So let's copy and let's have a look. Oh, sorry. That's because I don't have that one. There we go. So I have to select mine, in this case, simple meter. This generates, in this case in the URDF, so if I go here, we can see that it generated a PDF. If we download it, you can see that it's more or less very similar to the TF trees that we can print with RQT, but the difference is that it's giving us the joints, and this is really good when you have very complex robots and you want to understand what's the structure in it. Yeah. Okay. So I think that's about it. So what I want you to do is play a bit, change the geometric shapes, move around the joints, change the axis, and change also the colors. So what's the basics of a link is this. So the origin and the geometry. The origin is important if the geometric shape is, you want to move it from the center, which is not normal. Normally you use this for three-dimensional models that we'll use at the end of this unit, but normally you don't use it with geometric shapes. And another thing that it's really interesting is giving colors. So in URDF you just have to define a material name and the name that you want, then RGB color, RGBA, and then you define it just below the geometry. You say material name green, and that's it. So let's have a look at the morphology of the robot. So in this case we have a head, a base, then we have a roll, pitch and yaw system, and we have a camera and two eyes. Yeah. So these are the main elements that we want to define to create this robot. Here are some photographs of what it should be made of. So you can see that inside we have this system. This system is just to connect the base with the head in a roll, pitch and yaw system like you see here. Yeah. It wouldn't be necessary to visualize it, but it's really useful to see it, because this way you know if you're doing it right. and it's working. And it has no effect in the simulation, because when you simulate it, you won't put any collisions, or you'll put very, very, very small inertias. Yeah? So, the next exercise is create the robot with geometric shapes. And here you have some data of how to do it, the dimensions and where to put it and so on. Yeah? But I want you to try and see how difficult it is without where to put it. Yeah? When you're finished or when you get stuck, continue and you'll see the solution. So let's spawn this. So we are going to select, let me see, so I have this one in this case, meta only for URDF, no dies. So here I defined all of it. You have the solutions in the at the bottom of the exercise. But basically it's just putting more links and more joints and some colors. That's more or less it. So let's have a look how it should be. So we go here, we use our, oh sorry, we have to close this. Yeah, you can save them if you want. I have my own, so, and you can save those files so that it's not, you don't have to put it every time. So we go here and we spawn. Again, I'm talking about spawning, but you're not seeing anything because we're not using the simulation for the moment. So here, again, you'll have this, put it on the top, then double click here, going fast, then select your RVIZ configuration that you saved before, and in my case I have it here, and say nope, and there you have it. So let's make the TFs a bit smaller, because otherwise it's too big. Yeah, so here we have it. So it's a basic geometric shape, but we have the morphology right. So we have the base and the head, and it moves around as it should, right? We have the roll, the pitch, and bear in mind that if we pitch here, the roll depends on it. So it's important to see that. And the yaw depends on both. Yep. Perfect. If you got here, congratulations. Now the only thing that we have to do is just change this geometric shapes to some 3D models that we've created. In this case, we give it for you, but you can use any 3D model that you want. So let's have a look. So we go here and let's have a look. How do you do that? So the first thing you have to do is execute this command so that you can copy the models that we have here in the system to your workspace. Then you have to go to meta description. Let's show it here. So in your package, you have to create a folder called models, inside it one called meta, and inside it one called meshes. And inside it, of course, you can have another structure. It's just that this one is the one that normally people use. So here you have the models. These are 3D die models created in SolidWorks that were ported then with Blender. If you need some tutorials, we have a video talking about that. And so basically what we have to do is in the geometry tag, replace the one that was cylinder or box or sphere with this line: mesh, file name, package, my meta description, models, meta, it's all the path from the package until the file. And that's it. So let's have a look. So in my case, the URDF that I use is this one. There we go. So this one has all the things needed for visualization in RVIZ. So I am going to copy this one and execute again our fantastic program. It's essentially a launch. There we go. This is very important that there's no error, that it finds the packages and so on. Again, be careful with this. Then you can also use recently configs. So there we go. Discard. And there we have it. So if we get, yeah, we have the meta robot. So you can move it around. You must see that there's no collisions, that the three-dimensional shapes don't overlap. It seems okay, yeah. It's a very good practice. Just put it in the extremes, so in the maximums, to see if there's a problem in the model. And see, okay, there's nothing strange about it. And it's more or less as the real robot, let's say. So it's okay. Yeah? Fantastic. So now we're done with unit 1. So in next unit we are going to learn how to go from this fantastic URDF model to a physical representation and simulation of this robot. So you'll have to add mass, inertias, and also we'll add motors to move the robot around. And at the end, we are going to learn how to add sensors, in this case, a camera. So let's go. Okay, welcome back. So this unit, what we are going to do is adapt our URDF model to Gazebo, because it has some things that you have to add so that it can be simulated. One are collisions. Why? Because otherwise you'll have a ghost, you'll have a robot that doesn't collide with anything, even with the floor. So if it weighs but doesn't collide, it will just go through the floor. Yeah. So this is really important. So the collisions are added in the link. In this case, they are very similar in morphology. Actually, they are exactly the same as the visual tag, just that it's collision. But you put geometries, or you can put also meshes. Normally what we do is we use simplified versions of the models in the collisions, or we just directly use geometric shapes. Geometric shapes are more efficient than 3D models. That's why we use them, because physically it's much easier and computers go faster. And essentially, normally it's more than enough. It's only useful when you need a very specific geometry that you have to use a 3D model in the collisions. Yeah, so you can use them like this. So, and this is another example that it's with low polygons. So it's the same version, so it's the same model, but this version is low polygons. So it has much less polygons, because for collisions is not needed so many. Okay, but the thing is, okay, but how do I put my robot in the simulation? So that's what spawning is all about. So you have this launch file which spawns a URDF file. First, it's loaded into the robot description, and then the robot description is used to spawn the robot in the world, in the position that you want, through the URDF spawner. It's the package Gazebo-ROS, and it's the spawn model binary. Yep. So you have to create a copy of this launch file in your package, and then I recommend you just to create this spawn Mira launch, which spawns your robot, which uses this include spawn URDF and with parameters. That way you can use it for other robots, for example. Yeah. Okay, so exercise: add the collisions and spawn the robot, and tell me what happens. Bear in mind that you don't have to put collisions in every element, because some elements don't need collisions. Ready? Okay. So if you did it correctly, and you launched, something happened. You didn't find the model. That's because Gazebo needs something else to spawn and simulate the robot. That thing is inertias. But if you execute this command, you'll see that you have a robot. You have the Mira model. So let's do it. So if we go here and we go to the launch and we spawn Mira, and I'm going to spawn, for example, my model, no inertias. And then I go here and I do ROS launch, my Mira description, spawn Mira. What happens is that it says that successfully was spawned, and there's a message here that something was spawned. And if you go here, maybe you can tap it. But the thing is, it's not here. But then why, when I go here and I execute this call to see what models I have in the scene, it happens that you have the Mira robot. That's because you didn't put the inertias. It's a very common problem and something that we all have forgotten once or twice. Yeah. So to delete this model, just execute this command or use a Python, whatever you want. Just you have to call this service. You go here, you execute this, and there we go. Sometimes it does, normally does. If it doesn't, you just have to restart the simulation, but normally it does it, no problem. There we go. So now we don't have the model. If we check here, we don't have it. Okay, so let's add the inertias. So let's have a look. How do we add the inertias? So inertias, it's a very tricky theme, especially when you don't have any dimensions and measurements of your robot. You have to know the mass of that link or an approximation, and then you need to know the inertia moments. You have to calculate them. How do you calculate them? Normally you simplify and say, okay, it's a cube, it's a cylinder, and you use some formulas. We have provided for you a program to calculate the basic geometric shapes, which are box, spheres, and cylinders. So if, for example, I go here and I have it already here in my scripts, inertias calculator. So we do ROS run my Mira description, inertias calculation, and then I select, for example, it's very simple but has a job done. I put the mass 12 kilos, then the width, say 1, depth and height. And then it will give me the dimensions, so the moments of inertia. This would be the I x, then this is the y, and this is the z in this case. Yeah? But you can do it for spheres and cylinders, or for any other shapes, but that's up to you. So, once you have it, then another thing that it's important to add is some elements have to have friction and dynamic effects that they have when you apply a force. So this is very important for friction and how they get squashed when you apply a force, static forces in this case, or dynamic forces. Yeah. This is very important, especially in the second model that we'll create, which is GURDI, that has slightly squishy feet. That makes that it gets stuck to the ground. Yeah. But the most important thing here in this case is if you want to put colors in Gazebo, you'll have to define a material inside this Gazebo tag. Otherwise, the colors that you defined before won't appear in Gazebo. Okay? You have more details of all the coefficients of what it is and so on. Yeah. So, exercise. Put the inertias of all the links and spawn the robot. Once you have it, you should have something similar to this. So let's do it. So for this, I'm going to spawn meter, and I'm going to spawn this one. Yep. Yeah. There we go. And let's spawn. Yeah, finally, the first time that we have our robot inside the simulator. As you can see, because it has weight, it tilts, and because there's no friction in the joints, it will stay moving forever and ever, and it's limp. That's because there are no controllers still active. And that's the next step. So let's go for it. So before that, I'm going to delete the model. I can delete with right click and then delete. There we have it. If we want to check that it's gone, there we go. If we execute the ROS service call of the get world properties, we'll see if it's there or not. Yeah. So the next step is adding controllers. So you have all the solution here. So no problem if you get stuck. So adding controllers. Adding controllers has some steps. We talked about this a bit in the TF course, so if you've done it, I think you'll understand it much better here. But essentially what you have to add is first the plugin, which is the Gazebo-ROS control, and you have to state the robot namespace. I recommend you to put the same name as the robot model. It's much easier and simpler. And then it's always the transmissions are connected to a joint, of course. A joint that moves, so a revolute or a continuous or prismatic and so on. So the first thing you have to say is, okay, I have this transmission. I define the type, in this case simple transmission, and this is really important, the joint, so roll joint. And then the hardware interface, in this case it's effort joint interface, which is the one that works and actually is the one that normally all the people use. And if you need a mechanical reduction, then, but normally you don't need it. Yeah. And here is where these values of the joints are becoming really important, because now here you're defining the maximum effort that that joint can cope. So this is the maximum effort that you'll get, and this is the maximum velocity, which means that if you don't get this data right, you'll end up having robots that move so fast that they fall or they fly. So you have to get this right, the physical and most accurate number as possible to reality. Once you have it, then you have to define in another file called meter control YAML the control parameters, which are basically the PID values and the rate in which we publish, okay, in which joint state controller publishes. So here you put the namespace, in this case meter, and then inside it you put, as you see, the joint state controller, and then all the different controllers. So if we go up a bit, so here we are stating the joint in which is connected, and here we are stating, okay, this controller, we are creating this name right here, and it's related to this joint, and it's using this type of control, position control, so that values that you send to the command, to the joints or whatever, are positions. They are not speeds, they are not efforts, they are positions. But you can do also speed or effort control. Okay? Another tool that it's really important is RQT reconfigure. This, I'm going to show you working, allows you to configure the PID values on the fly, which is absolutely necessary in the first steps that you design a robot, because you'll probably get it wrong. So you have to tweak them until the robot moves as it should. And the third step, you have to create this launch that launches all the control systems. So it loads the YAML to the ROS param, then the controller spawner, you start it, and you state here all the controllers that you want to activate, and you specify also a shutdown timer in the case that, for example, you delete the robot, then 3 seconds in this case, it will stop the controllers working. And then we do a robot state publisher just to have the joint states and so on for the RVIZ, basically. Yeah? There's a warning here. Be careful with the namespaces, because especially here in the controller, it's really sensible for that. So be careful. Okay. Once it's done, you just have to launch the controllers and spawn the robot. That's it. Nothing special. Okay, so let's do it. So you go here, you create your control, in this case meter control. You have it here. Then you create in your config folder, you create this meter control YAML, which is here. You can set the syntax. And finally, in the URDF, you have to define all the transmissions and so on. Yep. So let's have a look. Let's do spawn with controllers. In this case, let's do spawn with one controller only. So spawn mirror. Let's select the URDF with that defined. So one controller. So once we've changed this, we just have to launch this this one, spawn with one controller. So let's have a look. ROS launch, my meter, spawn with one controller. So there we go, there we have it. So now, as you can see, it's moving, but it's moving because the only joint that we activated was the roll. So let's move it. So here you have some options of what you can do to move it. So there are two options. Or you publish directly in the topic. You also, of course, if you can publish a topic, then you can use a Python module, a Python program to publish, no problem there. Or, in this case, we highly recommend to use RQT GUI because this allows you to test very, very fast if your controllers are working and test different movements. Okay, so we have this. Now we select, let me see, mirror roll join command, exactly. So now we add this and we can put, for example, we can put values, but this is a very good way of testing if your model is correctly done. So we will send values based on the time, which is I, divided by 100 because we are publishing at 100 Hertz, and it will send incremental values following a sine wave. So we click here and there we have it. So you see it moves one side to another one. This is the roll, so this is the movement that it should do. Yeah. Okay, fantastic. So now we can deactivate this and we can, well, we don't have to close it actually. So now it's your turn. So now you have to add controllers for the other two motors. So the tilt and the pitch, let's say, pan, or the pan and the pitch also, and do exactly the same process I did, but now with the three. When you finish or you get stuck, you just have to scroll down and you have the solution. Yeah. So you should get something similar to this. So if we select this and we go to the spawn URDF, so spawn meter, and we select the meter, in this case without sensors, which is with all except the sensors, the cameras and so on. You should get something similar to this. So I'm going to launch controllers. So what's the main difference? The main difference is that you have to launch, you have to activate all the controllers. So you can see here that I have mirror control and one controller. The difference is that here I'm activating the roll, but also the pitch and the yaw. Yeah. So now I have full control. You see, it's not moving. That's a very good sign. So now here, if we refresh, we can get the pitch. There we go. And also we can see the yaw. Oh, sorry. Where is it? There we go. The yaw. And we add it. Then we add the same function, the sine function. That way we'll see all the values that can take the joints. As I said, is a very good way of seeing if your system is working. So now we activate it, and we should see that it's moving around in pan, tilt, and yaw. Yeah, perfect. So now there's only one thing that you have to learn, is the fact that you can also add sensors. Here you have an example of movement with Python. You can have it take a look. So the last step is adding sensors. There are many sensors. You can put IMUs, you can put cameras, you can put any sensors that you can imagine, lasers, Kinect sensors, so on. In this case, you have here an example of how to add a camera. I'll just comment on the very important aspects. One is the rate in which you publish the camera, and the other one is the format. In this case, we put 400 by 400. It depends on the power of your computer, and in the case of in case you do it in RDS, in our systems, or in a cloud-based system, you have to know all the capabilities that you have in that system, because if you put too much, maybe you'll collapse the system. Yeah, 400 by 400 is more than enough in our case. Yeah, okay. Just comment one thing. There's an issue in Gazebo which makes that when you stop a robot and you delete the robot from the simulation with a plugin inside, some plugins, and this is one of them, the camera one, it crashes. It makes Gazebo crash. In your local system will crash the system, and you'll have to restart the system again. In our system, it is probable that you won't detect it, because our system, when Gazebo falls, it will detect it and relaunch again. But in case it doesn't, because it stays there forever, there's a way. If you try to reset a simulation to do a ROS service call, it will kill any zombie systems that are around. Yep. So congratulations, you now know how to create a robot from scratch. So what's the next step? Well, the next step is, first we are going to clean up this a bit. So we're going to delete meter, and let's close this also and click next. So the next unit is about Gurdi. Gurdi is a 3-legged robot that moves around and it's a bit more complex than the one that you've done, but this is to exercise, to practice how to build a robot from scratch, and more complex than the one you did before. Here you have some hints and some details of how to do it. So you have all the data necessary to create this robot by yourself, and this is the exercise that you have to do. You have some data very useful, like for example the structure, or here the links and joints structure, which is more detailed, very important. You have also the dimensions for the very difficult part, which is connect the legs to the head, let's say. So that's quite important. Then you have where to get the files also, and everything, and also how to add the plugin of the IMU. So go ahead. You also have some values to have an idea of what order of PIDs you need for control. Also, you have the weights, dimensions. So once you've done it, if you get stuck, you have a solution here. It's only a solution. You can do it as you wish. You can add legs if you want. That's the great part of this. Yep. So here you have all the solutions, and you have also the launch file for the control, and also the demo file that moves the robot around. And you should get something similar to this. So let's launch it. So if we do ROS launch, in this case I did a package like the meter, and here we have spawn with controllers. So my Gordy, but the structure is exactly the same as the meter. Spawn with controllers dot launch. There you have it. So you see it's rigid, so the controllers are working, and now we can launch. You could do our RQT GUI, of course, but in this case it's more difficult because they have to be coordinated. So let's do the demo. Sorry, it's ROS. There you go. This robot has a very good system geometry because it's very difficult that it gets upside down, and if it falls, by closing the legs it restarts to the position. It's really nice. Yeah, and you can see the frictions, and you can try changing them and putting extra legs and so on, or even adding joints. For example, let's stop him, because so you can try to make another joint here so that it can rotate the legs. So you can try anything, and if you want to learn, try and change and experiment, because it will help you a lot to understand. And that's quite it. This unit is just showing you what you should get and what you have here in the unit. So finally, let's cancel this, delete him. Okay. The problem is that if you use only URDFs, you can't, it's very difficult to maintain a very complex model of a robot. So chakras were created. Chakras are macros basically, and what allows you to do is, for example, in the Gurdi, because there's symmetry and basically it's three legs exactly the same, you can use macros to define only one leg and then copy it around. But chakras, you can use them for many other stuff. For example, you can define constants, you can define variables that you can change faster, and that way you can change your robot model very, very fast. And you can put ifs. It's very, very powerful. Here you get more or less the basic concepts and the basic applications of chakras. Yeah, so the constants and basically the macros. And also math is really important. Like you have the pi constant and making some, you can do some calculations. This is very good, for example, for inertia calculation. so that when you change the mass, you don't have to recalculate every time with an external program. You just put the formula here, for example, and it will recalculate everything. So it's very, very practical. So we'll scroll here. So the exercise is just use all this of the macros and chakras to change the model and do a chakra version. There is some special stuff that you have to know, and here you have the solution, but it's very important that you know how to spawn a chakra. Here you have an example of how you spawn chakras. It's slightly different from slightly different from URDFs, but basically it's the same. You're loading the chakras, you're using the chakra binaries to execute and read it, and then decode it and put it in the robot description. And basically what it does is create a URDF. Yeah. So just point out some stuff. For example, here you can see the use of the chakras. Here, for example, let's have a look. Here we are defining this chakra that has as input the number, and it's the upper leg link. So this one, we will use it for the 3, and we'll just have to give it a number, so 1, 2, and 3. We also, for example, use this foot link, which has 2 variables, number and color. So the number that changes the names, and the color that changes the color here. Here you go. Okay, and this allows you to do this. Here you have the definitions. Some things I've left it as they were, but others, for example, here we're defining the upper leg link, the number 1, the 2, and 3. Then we have the joints, and then here again the links, lower legs 1, 2, and 3, and also the foot. So it makes the code cleaner and easier to maintain. Yeah, because for example, here you only use this dies once. In the lower leg you use it once. In the model, in the URDF model, you used it 3 times. So if you change the model, you have to change it 3 times. Yep. Okay, so that's it basically. So now, very fast, the final project is you have to create the Gazebo URDF, or chakra in this case, by yourself. We don't give you any data whatsoever, and the only thing that we give you is the 3-dimensional models. But other than that, you'll have to decide how many links you have, you'll have to decide which type of joints, the controllers, the PIDs, everything. So it's a project, very fun project, and you can use it also to add cameras. You can use it also then to do other projects like face recognition and other stuff. So we would be delighted that you send us your findings, your projects that you do with Gazebo. And that's quite it. So when you finish, what can you do? So you can go to ROS Development Studio, which is here. You have to go to here, the construct page, ROS Devel Studio, and get started or sign in, and you'll get something like this. So you have a space for private simulations and one for public simulations. In the public space, you have many simulations. Some use Gazebo Simulator and the others use Webot Simulator. And you have very interesting simulations like drone simulations, BB-8 simulation, grasping simulations, OpenAI Gym, massive simulations also. Some of webs are really interesting, so check them out. And again, if you want to learn more, just go to Robot Ignite. So if we let me log out, so you have many courses here that you can do ROS in 5 days if you have problems with ROS basics, or I highly recommend you that you do TFs after this course. You'll learn a lot. You can also learn a lot of mapping and navigation in our courses made for navigation. We have 2 courses, very good ones. Then we have also ROS Industrial and also Control, very good one there. And if you're interested in OpenAI Gym, we have a special course for that, and also an autonomous vehicles course. And also we have video versions of that courses, as the one you have already watched, this one. And apart from that, thank you very much and hope to see you soon.